Hi, I'm going to explain the DES algorithm. In this presentation, I'm going to explain a brief overview of the algorithm, some features, and how it works. First, overview. Data encryption standard DES is a block cipher that uses shared secret encryption, developed in the early 70s at IBM and based on an early design by Horst Ferstel. It was selected by the National Bureau of Standards as an official Federal Information Processing Standard (FIPS) for the United States in 1977. It is based on a symmetric key algorithm that uses a 56-bit key, and this algorithm was highly influential in the advancement of modern cryptography in the academic world. DES is now considered to be unsecure for many applications, and this is chiefly due to the 56-bit key size being too small. So, some features of this algorithm that I'm going to explain a little bit are architecture, security, scalability, flexibility, and some limitations. So we can see here a chart with different algorithms, and we can see how are the different structures, the plain text, key size, the number of S boxes that I use, and number of rounds. In our case, DES use a physical structure, plain text of 64 bits, a key size of 56, use 8 S boxes and 16 rounds. This algorithm is based on the backbone concept on physical structure. As I say, it uses 64-bit plain text with 16 rounds and a key length of 56 bits. Originally, the key is of 64 bits, same as the block size, but in every byte, one bit it has been selected as a parity bit and is not used for encryption mechanism. So the 56-bit is permuted into 16 subkeys, each of 48-bit length, and it also contains, as I say, 8 S boxes, and the same algorithm is used in reverse for decryption. So we have another feature that is security. In the case of DES, the security strength depends on its 56 bits key size, generating 7.2 per 1016 possible keys, making it extremely difficult to originate a particular key in typical threat environment. Moreover, if the keys change frequently, the risk of unauthorized computation or acquisition can be greatly moderated. In general, DES was proved insecure for large corporations or government. However, for backward compatibility and cost of upgrading, DES should still be preferred, outweighing the risk of exposure. So now let's see for scalability, this graph that shows generic scalability, memory usage, that is in red color, and the encryption performance, that is in blue. As we can see, this algorithm use no more memory usage than the cipher encryption performance. And now let's talk about the limitation of this algorithm. DES is highly vulnerable to linear cryptanalysis attacks. Weak keys is also a great issue. DES is also exposed to brute force attack. So next we are going to discuss how this algorithm works. DES algorithm has two main processes. One of these processes is the generation of keys. Let's see how it works. I'm going to explain the generation of key in some steps. The first step is that we are going to take our 64 bits key, right here, and we are going to permute it according to the PC1 table, that is this one. Permuted means that we are going to make some changes in the order of our bits. we are going to take our key of 64 bits and we are going to make a reorder of the bits. So in the first place of our permuted key, we are going to have our 57 bit. In the second position, the bit number 49. In the third position, the bit number 41, and so on. And our last bit is going to be the bit number 4 of the 64 bits key. It's important to know that on our permuted key, we are going to have only 56 bits because the table only have 56 bits. The second step is permute the key into two halves that we are going to call left and right halves. The third step is that we are going to form from a first pair L0, R0. In this case, this will be our first pair L0, R0. And we are going to form from this pair 16 blocks of the pairs Ln, Rn. And each pair of blocks Ln, Rn will be formed from the previous pair, which will be Ln-1 and Rn-1. So, using a schedule of left shift of the previous block. But what means a left shift or how it works? It's simple. We are going to move each bit one place to the left, except for the first bit, which is cycled to the end of the block. As we know, the ES algorithm works with 16 rounds or iterations, and in each iteration we are going to have a specific number of left shifts. In the first iteration we are going to make only one left shift, and in the second iteration only one left shift. But in the iteration number 3, 4, 5, 6, 7, and 8, we are going to make two left shifts. In the iteration number 9, only one left shift, and in iteration 10, 11, 12, 13, 14, and 15, we are going to make two left shifts. And in the last iteration, that is number 16, we are going to make only one left shift. The fourth step consists of form the key Kn by applying the permutation of the table using the table PC2 to each pair that is concatenated using the left and right half that is called Ln and Rn. Each pair has 56 bits, but the table PC2 only uses 48 of these bits. So when we concatenate the two halves, in the first position, the key N is going to have the bit that was in the position 14 in the first place. In the second place, it will contain the bit that was in the position number 17, and so on. And in the last position, the key will contain the bit that previously was in the 32 position. As we can see in this diagram, we are going to have a key of 64 bits as an input, and this key will be permuted with the table PC1, and then this new key permuted will be split into halves, and these halves are going to have left shifts according to table that says that if we are in the first iteration, we are going to make one left shift. If we are in the second, one, third, two, and so on. And after that, we are going to apply the PC2 table, that is this one that we have here. So let's take a look now to the second part, that is fractioning of that text. We are going to take our 64 bits message and we are going to apply an initial permutation. Our first bit in the permuted message will be the 58 bit, of our original message. The second bit will be the 50 of our original message, and so on. Our last bit will be the 7th bit of our original message. We are going to split the permuted block into a left half that we are going to call in this case L0 of 32 bits, and a right half that we are going to call R0 of 32 bits too. For the next 16 iterations, we are going to obtain Ln and Rn. In the case of Ln, it will be equal to Rn minus 1, and Rn will be Ln minus 1 XOR the f function of Rn minus 1 and key n. So if we are going to work in the first iteration, L1 will be L1 minus 1, so L1 will be R0, and R0 will be L1 minus 1, so it will be L0 XOR the function of R0 and the key 1. And how we can obtain the f function? We have to make an expansion of the Rn minus 1, in this case R0, by using this table, and after that we are going to get a result. That result we have to XOR with the key 1 in the case of the first iteration. Now we're going to work with our results and with the Xboxes. As a result of our XOR between the key and the expansion, we get 8 groups of 6 bits each one. Imagine that one group is 0, 1, 1, 0, 1, 1. This is our B1. So we want to obtain S1, B1, and what we are going to do is that we are going to take our first and last bit, in this case 0 and 1, and this combination will represent a row in the S1 box. In this case, 0, 1 in decimal is 1, so it means that we have to work with our row number 1, and then with the middle 4 bits, in this case 1, 1, 0, 1, if we convert this binary number to decimal, we get number 13, so it means that it will be our column 13. Row 1, column 13, we obtain this number, that is 5, and if we convert number 5 to binary, we have 0, 1, 0, 1, and this is our result of the S1, B1, and we are going to do the same process for S2, B2, S3, B3, and until S8, B8. And the final stage in the calculation of f function is to do a permutation P of the S-box output. So we are going to use this table, and we are going to permute all the results that we get in the previous step. When we obtain R16, L16, we reverse the order of the two blocks in a 64-bit block and apply a final permutation. For this permutation, we are going to use this table, and as in the previous cases, our first bit will be the 40-bit, the second bit will be the 8-bit, and so on, and our last bit will be the 25-bit. The result of this operation will be our ciphertext. For decryption, we use the same algorithm, but reversing the order in which the subkeys are applied.